Okay, I'm a morning person, but I'm not usually 3 hours ahead, so I hope this is coherent. So we're one of the smaller teams. There are just two of us, postdoc Mario Flock and me at JPL, and we're working on the planet-forming environment close to young stars, the very inner parts of protostellar disks. So we want to learn about the environments where systems of close planets like these ones around Kepler-11 may have either formed in situ or perhaps migrated after forming further out. And we're modeling the protostellar disk's innermost parts. For the first time, we're treating the gas dynamics alongside the heating from the starlight and the sublimation and condensation of the silicate dust particles, which are both the main raw ingredient for forming terrestrial planets and the cores of gas giants, and also the source of opacity for absorbing the starlight. So there's a key interaction there between the starlight and the silicate dust. And what we're looking at here is a synthetic image of a snapshot from one of Mario's models. So there are, whoops, let me see if I've got this right here. Yep, okay, so you can see the three different color bands that are combined to make this image, and the longer wavelength one, making this red circle here, is showing the shape of this silicate sublimation front. So there's a star at the center, not shown in this synthetic image. And we're primarily seeing reprocessed starlight just after it's been absorbed and then re-emitted from that silicate destruction surface. Okay, we're testing the models against observational constraints like this one, where an infrared interferometer was used to measure the size of that sublimation ring around one particular star by Miriam Benisti and company. And here's a cartoon summary of Mario's modeling results. So nearest to the star in here, it's so hot that everything is gas. You go a little bit further out and you're into the regime where whether you have dust depends on the pressure. Near the midplane where the gas pressure is high, the silicates can survive a little bit nearer to the star. Up in the atmosphere, where the gas pressure is lower, you have to be further away from the star before the material can survive. And so when you're looking in a meridional cross-section like this, you get this sort of nose that's pointing at the star. And it's the top surface of that nose that we saw a couple of slides back. And because this material is receiving direct starlight, it's extra hot, which means it puffs up. It gets a little bit thicker, perpendicular to the equatorial plane. And because it's thick, that means it casts a shadow on the stuff beyond it. And as a consequence of that, we have a local pressure maximum. If you go outwards in the midplane here, there's a local maximum in the pressure at this location. And that's important because it means that solid particles outside or inside the pressure maximum will spiral to that maximum and sit there. So it's potentially a place where we could build planets. But it's very different from the planet-forming environments we're used to thinking of, because the temperature is about 1,000 Kelvin and conditions are more or less like what you get in the outer layers of a hot Jupiter's atmosphere. Oh, another thing, so it's been suggested that the sharp pressure jump that you have where you go from hot and starlit to a bit cooler and dark might destabilize. This might be dynamically unstable, this front. But in Mario's calculations, you run for hundreds of orbits and it just sits there quietly. So at least under axisymmetry, which these initial calculations assume, it's stable. And the next challenge is, of course, to go to 3D and begin to include the effects of the magnetic fields, which will stir up that material. And perhaps it won't be so stable anymore once we include that. Okay, the rest of my time here is about some collaborative activities that have happened in the last year because of NExSS. So the first one was I had a 4-day visit to the Arizona State NExSS team. I gave a seminar and discussed possible proposal ideas with Steve Desch and his colleagues there. And one of the things that came out of that is, so there is a movie here. I took a chance, but it doesn't matter too much. So we discussed ideas for how to make the dimmings in Tabby's star. In particular, several of the dimmings have a slow ingress. So the dimming begins slowly and then gets stronger. And that's a little bit difficult to explain if you have some sudden production of dust and the dust is on Keplerian orbits, or even if you have radiation pressure affecting the orbits. But perhaps you can explain it if the star's magnetic field is acting on the grains. In particular, the grains should quickly be charged by a photoelectric effect, and then they can be perhaps whipped around by the magnetic forces. So we'd like to look into that, and our proposal to JPL's University Partnerships program is pending. A third collaboration over the last year, so Hannah Jane Condell has agreed to send her graduate student Dylan Kloster to us for the summer. He's going to work on how we can distinguish young planets from other features that you might see in planet-forming disks. He's supported by the Wyoming Space Grant Program. A fourth thing came out of a conversation I had with SETI Institute NExSS PI Hiroshi Imanaka. He was telling me about his haze experiments, and that got me thinking about what sort of lab measurements we would need to do a better job for the protostellar disk models. And I learned that my JPL colleagues Mercy Gudapati and Brianna Henderson over here, they have a new furnace in their lab which can reproduce pressures and temperatures found in the inner part of protostellar disks near the silicate sublimation front. And so we have an exoplanet research program proposal due on Thursday. Still needs some work, but we would like to take various mixtures of materials, perhaps representing the elemental composition of what's been seen, for example, in the stardust sample return, and we'd like to heat them up to the sublimation point and cool them down again, and see what we get out and measure its optical properties. That could then become input for the next generation of the protostellar disk models. And then the final thing is that we are ready to offer two multi-Nexus node opportunities through the NASA postdoc program. First one is with Penn State and Arizona State. We'd like to get probably an observer, but hopefully I can convince them to do some modeling too, to try and understand Tabby's star and look for other similar events. Probably they'll be very diverse, but we'll try to find some kind of unifying theme. And then the second NPP position is jointly between JPL and Arizona State on looking at how gas-rich planets got their heavy element enrichments relative to their stars. That's all. Thank you very much.